Yeah, Karen, we are before you talk, so I can ask you a very naive question. What is a digital twin, and why do we need such twins?
So what is a digital twin? It's a virtual representation, or if you like to think of it as a computer model and computer simulation of a physical system. So think of your favorite physical system. For me, that would be an aircraft or a spacecraft. So it could be an engineering system. It could also be something in the natural world, or it could be a human. This could be a medical digital twin. And what's special about the digital twin and what makes it different to the computer simulations we've been used to is that this digital twin, first of all, is personalized. So it's not a generic model of a heart or a generic model of an aircraft, but rather it's a personalized model of your heart or my heart. Mm-hmm. And that personalization comes because the digital twin is connected to the physical system, and there's a feedback flow of data from the physical system to the computer model constantly being dynamically updated so that as your heart, the properties change, the digital twin can change with you and follow along. And then the last really critical piece is that this digital twin now can be used to drive decision making. So it can be used to make predictions, again, that are personalized to you, the individual, or personalized to one particular aircraft, so that decision makers can make decisions about things like predictive maintenance, when to go in and have a scan on your heart, or when to take an airplane in to have a scan. So it's really that connection between the physical world, the virtual world, with the data and the decisions connecting the two.
That's interesting. I was thinking about applications in engineering, but there could also be applications in medicine. Is that true? For instance, the future of medicine, perhaps.
So the notion of a digital twin has its roots in engineering, and in fact in aerospace engineering, where the term was first used. But I think personalized medicine is one of the most exciting places where we could see digital twins really as a way to move towards personalized medicine. And in fact, when I give the talk today, I'm going to talk about some of the work we've been doing in collaboration with the oncologists at UT Austin and building cancer patient digital twins, which is really fun.
You're between the disciplines, let's say, with mathematics and engineering. What do you feel more like a mathematician or like an engineer?
Oh, this is a great question. So I often joke that I am not a real mathematician, I'm not a real engineer, and I'm not a real computer scientist. Okay. And actually, I live somewhere between the three. So, in my group, some of the work is more applied, where we're really collaborating with industry, especially with the aerospace companies, and there we are doing engineering work focused on bringing mathematical modeling and computing to engineering. And then other parts of my research are more mathematical, more applied math. So I think that's what I really enjoy, is living between the two and being neither.
Perhaps you could give us a practical example where, for example, astronautics benefit from your work. What is a concrete application, perhaps?
Yeah. So a lot of the work that we do is in reduced order modeling. So this is a set of mathematical methods that aim to reduce the computational cost of simulations. And as one example, we're doing a lot of work with the US Air Force right now in trying to get reduced order models for rocket combustion. So these are the engines for current and future rockets. And this is an area where the Air Force has been investing a lot of work over the past decades into creating powerful mathematical models and computer simulations. But the problem is the computer simulations are so expensive. So if I wanted to do a simulation of an entire rocket engine on a supercomputer, I would be looking at weeks, maybe even months, for a single simulation. And of course, if I'm the rocket designer thinking about the next generation of vehicles that are going to take humans to the moon, back to the moon and to Mars, I don't want to do just one simulation. I want to do thousands of simulations because I'm trying to explore the design space. I want to be able to change the geometry, change the operating conditions, change the injection strategies. And clearly, if you have to wait 1 month for every simulation, this is not useful in a design setting. So we've been working extensively with the Air Force to try to come up with reduced order models, and this is where the power of mathematics really comes in. The physics are in the simulation, but mathematics now can come in on top of that and find low-dimensional structure, extract simpler models from these very complex simulations and then put them in the hands of a designer with times that are useful.
I read that you are involved in educational innovation. What is this? I've never heard of this.
This is really thinking about the way we educate the next generation of students, especially in engineering. Much of the way we educate, both in terms of the content, but also the pedagogy, the way that we teach, stems from the past. And if you think about the world that we are preparing these students to go into, it's a very, very different world to even when you and I were, especially me, when I was educated. It's a very different world. And so some of my work really thinks especially about how digital technologies can be used in education to improve student outcomes. So just like mathematical models and computer simulations have revolutionized the way engineers design products, they're playing a really big role in revolutionizing the way that we teach. So one of the things that I've really enjoyed doing throughout my career is to collaborate with people in education and to think about how do we bring mathematical modeling, data analytics, and computing to the classroom. And just as one example, one of the things that we've done is to map out curriculum. To your earlier question, you asked me, are you a mathematician or an engineer? And I said, I'm somewhere in the middle. When I first started teaching at MIT, way back in 2001, one of the things that really surprised me was how the students, I was teaching controls in the aerospace engineering curriculum. One of the things that really surprised me was that these students at MIT, one of the very best schools in the world, could not remember any of their math. Okay. They could not remember their calculus or their differential equations. And so that led me to realize that mathematicians and engineers use very different language to describe the same concepts. And engineering students taking math classes were not necessarily seeing the relevance. And sometimes the students would say to me, I didn't pay attention in math because I knew I wanted to be an aerospace engineer. So anyway, that led to me doing some work to understand how do we map out, how do we show students the connections between math and engineering. And from a mathematical standpoint, we can represent this as a graph. So we can build a graph that sort of maps out the space of what a student might learn in calculus and differential equations, and then see how those concepts have connections downstream in fluids and controls and engineering. And then once you have a mathematical model, once you have a graph, you can start to collect data and do inferences on a graph, and you can start to think about the way you deliver. So it's a fun side project.
Perhaps one word to the conference here. We are here providing a very broad range of mathematics. What do you think? How can you personally benefit from such a conference?
So first, it's a great honor to be invited to come to the conference, especially with it being focused on mathematics, and of course with the Hausdorff Institute to really represent that panorama of mathematics, everything from pure to applied, and then to people like me that even sit a little right of the applied. So to go back to what we just discussed, there's often a divide between communities, and I think even within our communities, we're often working on our pieces of the problem. We're thinking about our problems in a very particular way. We're using particular language. But of course, the grand problems in society are at the interfaces. And it's by interacting with people from other communities and seeing what they're working on and learning the language that they're speaking. I think by bringing these people together, that's how we're actually really going to advance the field. And honestly, it's such an exciting time for mathematics because the world is being revolutionized by computing. Whether you're in medicine or engineering or in the sciences or in societal applications, computing is revolutionizing everything. And of course, what are these computer models built on? They're built on mathematical models. And so I think the more that we can connect across that spectrum of the math community, the more chance we have of really tackling some of these big challenges.
Thank you very much for the interview.